Section 5.3, Topics from Number Theory. A proper divisor of a natural number is a divisor of the number that is not the number itself. A perfect number is a number that is equal to the sum of its proper divisors. The proper divisors of 28 are 1, 2, 4, 7, 14. Their sum, add those numbers together, 28. So that means 28 is considered a perfect number. Theorem says m sub n equals 2 to the n minus 1 is prime if and only if 2 to the n minus 1 times 2 to the n minus 1 is perfect. There are exactly the same number of Mersenne primes as there are perfect numbers. Remember that Mersenne prime rule from earlier in Chapter 5. Example, m sub 3 equals 2 to the third minus 1, which is 8 minus 1, which equals 7. 2 to the third minus 1 is 2 to the second times 2 to the third minus 1 is 7. We just wrote that. It's 4 times 7, which equals 28. And we just saw by listing the we just saw by listing the proper divisors that 28 is a perfect number. As of today, 50 perfect numbers are known. A deficient number is a number that is greater than the sum of its proper divisors. Example, the proper divisors of 10 are 1, 2, and 5. Their sum is 8. So 10 is a deficient number. An abundant number is a number that is less than the sum of its proper divisors. The proper divisors of 12 are 1, 2, 3, 4, and 6. The sum of the proper divisors is 16. 12 is an abundant number. 12 is less than 16, the sum of its proper divisors. Two numbers a and b are amicable if the sum of the proper divisors of a is b, and the sum of the proper divisors of b is a. The proper divisors of 220. Take a minute and list them. One, 2, 4, 5, 10, 11, 20, 22, 24, 55, and 110. Their sum is 284. The proper divisors of 284 are 1, 2, 4, 71, 142. Their sum is 220. 220 and 284 are amicable or friendly numbers. Approximately 12 million pairs of amicable numbers are known. Goldbach conjecture Every even number greater than 2 can be written as the sum of two prime numbers. Examples: 18. 18 is 7 plus 11, or it's 5 plus 13. 60 equals 23 plus 37, or 7 plus 53. It is a conjecture, not a theorem. It's not proved in general, but it's verified for all numbers up to 2 times 10 to the 18th. Twin primes. Prime numbers that differ by 2. Examples: 3 and 5, 5 and 7, 11 and 13, 17 and 19. The twin prime conjecture. It's a conjecture, not proved. There are infinitely many pairs of twin primes. As of today, the largest known pair of twin primes is right there. Pythagorean theorem, if you remember from geometry, it works with right triangles. In any right triangle with shorter sides, A and B, and longest side, C, the equation a squared plus b squared equals c squared will hold true. A triple, ABC, is a Pythagorean theorem triple if a squared plus b squared equals c squared. Examples of Pythagorean triples are 3, 4, 5, 5, 12, 13. We talk about triples, so we can talk about Fermat's last theorem. It was proved by Andrew Wiles in 1994. So really, mathematically speaking, not very long ago. For any natural number n greater than or equal to 3, there are no triples, ABC, that satisfy the equation a to the n plus b to the n equals c to the n. It only works for squaring a squared, b squared, and c squared.